Hi everyone. So in this video, I want to talk a little bit about the history of computer science. And I know that sounds a little weird. We're supposed to be learning how to program. What is it that we really get from looking at the people who lived hundreds of years ago? And the reason for that is that by looking at the big ideas that these visionaries had, we can start to see how programmers think and how we've gotten to the languages that we have today. So we are going to look at just a few key figures and see what their big contribution was to the field, and then look at how that gets reflected in any modern programming language that we look at today. So the first person that I want to tell you about is Ada Lovelace. So Ada Lovelace, who was born Lady Augustus Ada Byron, daughter of the poet Lord Byron, if you've heard of him. Later, she married someone named King, became Countess of Lovelace. Her mother was a huge proponent of mathematics. And so from a very early age, Ada was immersed in all of the great thinkers, the Enlightenment era thinkers, worked with them to tutor her so that she had a strong foundation in mathematics and the sciences, which was fairly uncommon at the time, but it did put her in contact with a lot of the thinkers whose writings on reason and mathematics have become foundational to computer science today. In particular, she worked very closely with the mathematician Charles Babbage. He developed the analytical engine, actually originally the differential engine, which was a big complicated machine for doing computations, simple mathematical calculations, at least by our modern standards. So you can see a proposed implementation of the analytical engine here. It had a bunch of levers, little tiny dials. You could input numbers, input a sequence of instructions, and it would have a mechanism for you to read out a result. Purely mathematical, basically the functions of, in today's terms, a calculator. So Ada, in working with Babbage, was tasked with writing out the instructions of how to use this machine to perform different types of computations. In particular, her big crowning achievement was a process that you could use to compute the Bernoulli numbers. So if you're familiar at all with math, they're slightly tricky to compute. The generally accepted easy way to do it is a process that relies on itself. It kind of self-references some of those instructions. And Ada Lovelace, in publishing her instructions for the analytical engine, came to a realization that so far they had been thinking about this machine in a very narrow perspective. They had been thinking of this as a simple calculator, but in reality, we weren't limited to just doing operations on simple numbers. As long as you could encode any process or any data you could think of numerically, somehow store it as a number, then you could use this same machine to do any type of work you could think of. In her notes that she left at the end of one of the memoirs she translated for Babbage, she had written, "Supposing that the fundamental relations of pitched sounds in the science of harmony and musical composition were susceptible to such expression in adaptations, this engine might even compose elaborate and scientific pieces of music of any degree of complexity or extent." What she's saying here is, if you could just figure out a way to write the instructions to get pitches that sound nice together, a computer could even produce music. It could produce sound that you could hear. If you've worked with computers or are watching this video on a computer right now, that might be very intuitive to you. But as far as we have in the historical record, Ada Lovelace was the first person to ever make that connection, that we can take sound, convert it into numbers, and then store it, process it, replay it from that numerical form back into something that your ear can hear. And that big idea that she had, that numbers can be an abstract representation of anything in the material physical world, that is hugely influential to the way that we store data in our programs and how we think about computers, not just as a computational engine, not just as something that can do math, but as something that can store a representation of reality. So the next person that I want to introduce you to is Alan Turing. So Alan Turing was a British mathematician and a code breaker during World War II. So one of the things he's most famous for was cracking the German Enigma code. This was the secret code they used to relay orders to their submarines, and it was a big challenge, and cracking it actually did create huge advances in the field of cryptography, which is very closely related to computer science. But the developments I want to focus on are the ones that lead to him being called the father of algorithms. So this term algorithms comes up in the media all the time when we talk about AI algorithms or any type of social networking algorithms, you know, the Google algorithm, the YouTube algorithm. All the term algorithm means in this context is just a series of instructions that we can follow to solve some well-defined task. So you can have algorithms not just for big websites, you can have algorithms for simple computational processes. Things like saying, figure out for me the best route to travel between these cities, or figure out the best things for me to get the most value at the grocery store, or schedule all these tasks I have to do in order. Every one of those can be solved with an algorithm that tells you how to do that particular task. So up until this point, every single time we had some new task, it was an open question, you know, what language can we use to describe this task? We have to basically create a mathematical proof from scratch to determine that we've actually solved the problem. Alan Turing's big contribution here was that he described a universal Turing machine, which was basically an infinitely long roll of tape that could have any number of symbols written on it, and a small camera that could interpret this symbol and, based on the symbol that was in front of it in the tape, somehow change its internal state, and then move the tape to the left or the right, or say it's all done. And from this starting point, he described how any other problem you can think of can be reduced to just instructions that you would give, that you would encode on that tape for this machine that could read the symbol and twist to the left and the right. This was important because it gave us a foundation to say, I've got some hard real-world process that I want. How can I pull it back in simpler terms into things I already know how to work with? He had a quote in a letter that he wrote, "A digital computer is a universal machine in the sense that it can be made to replace any machine of a certain very wide class. It will not replace a bulldozer or a steam engine or a telescope, but it will replace any rival design of calculating machine. That is to say, any machine into which one can feed data and into which later will print out results." So in this quote, he's saying the analytical engine of before was not some unique custom machine. It's a computational machine, and all computation is computation. Much like how Ada Lovelace described how any data can be stored numerically, Turing realized any problem can be solved computationally. Any procedure that we want to do, any task we have, we can describe it in a set of steps and take any arbitrarily complex thing and break it down into just these single steps, and even describe groups of steps and use them later. This is the foundation of programming, in a sense, that we've got the ability to take anything we want our computer to do and describe it as a chain of steps, one after the next. And the strategies of proofs of correctness that Turing came up with during his time are still used today. We still reduce things down from these novel, new problems we've never seen before into the instructions we already know and know about, know how fast they run, when they work, when they don't. And from here, things really started to take off. So the next person I want to introduce you to was Dr. Grace Hopper. So Grace Hopper was a 20th century naval admiral in the United States and a doctor of computer science. So she was pretty soon after Alan Turing. But her big contribution was that she's really what put the language in programming languages. Dr. Hopper saw that up until her point, programming languages were very bespoke things. They were unique to each machine that was built. That, you know, you had the ENIAC supercomputer as big as a room. You had to learn how to program for that computer. But when she looked at this newly developed concept of algorithms, she realized there was nothing about these problems that we were solving that was actually specific to the hardware we were working with. It would be really nice if, instead of learning how to write instructions for specific machines, we had some language that existed independent of the specific computer it was running on. And then we wrote a program that could take our language and turn it into those machine instructions. And in order to realize this dream, Dr. Hopper invented the compiler. So a compiler is a program that takes very high-level statements, things that read almost like the English language, and distills them down into things that run on actual hardware. Every modern programming language that we use today uses either a compiler that does this before the program runs, or an interpreter, which is like a compiler, but it's rereading, translating your instructions in real time. So this invention of the compiler was hugely influential because it meant now people could go and develop whatever type of computer they wanted, and then instead of having to rewrite every program from scratch when you develop a new computer, all you have to do is write a program that can translate the few instructions that exist in these high-level languages down into the instructions that actually work on your hardware. It takes a big, complicated problem and again breaks it down into just a few steps. If we can describe just these single steps that are defined in the programming language, which is only a couple of them, there really aren't that many, then we can run any program that has ever been written for that programming language for any device. And this was really her big idea, was that programmers shouldn't be working on hardware. They should instead solve their problems in simple, machine-independent language. Dr. Hopper had a lot of wit, and so she has a lot of great quotes about this. But one of my favorites was, what I was after was to bring another whole group of people to be able to use the computer easily. The people that used English, not symbols. It was my own understanding of the different kinds of people, and I knew darn well that most people didn't like symbols. And you had to give them something else to work with, and obviously the next best thing was English. And this led to her developing COBOL, the first high-level programming language, or at least one of the first high-level programming languages. And the big syntactic influence of COBOL was the idea that your program should almost have parts of speech. Each line starts with a verb, and then you have the noun that you apply that verb to. The other noun, maybe, depending on the verb, that provides the extra details. And you might notice these are the same terms that we use in English if we're talking about the parts of a sentence. And that was really her contribution, was if Alan Turing is the father of algorithms, Grace Hopper is the mother of programming languages. And these three big ideas, if we bring them together, we can sort of see how programming works today. So, numbers can represent any type of data: sound, color, visuals, images, videos, even abstract concepts like people. You can have an employee ID, a number to represent a person. You can have numbers to represent letters and text. So we can represent anything as numbers. We can then say, okay, I want to do something to those numbers that actually represent sound or people or videos. And I can break that down into simple steps. I can say, okay, well, taking that song and playing it back twice as fast, that sounds complicated. But somehow mathematically, there's going to be a multiply by 2 or divide by 2, take lengths of time and notes, compress them down. I can model that as simple steps. And then I can describe those steps in plain language instead of writing a really big, long math problem that tells you the expression of how songs are played twice as fast. Instead, I'll say, write out what I want the computer to do in something that sounds almost like English. And so modern programming languages, the way that they actually experience the influence of these three big ideas is that almost every programming language you'll learn, at least now, today, the decade this video is being recorded, breaks everything down into just 4 stylized sentences that every program is composed of. It's just a chain of these things, one after the next, combined, mixed together, run in sequence to solve your problem. And those 4 statements are assignment statements, function statements, conditions, and loops. And if you have those 4 tools, you know programming. Each one will write them a little bit different, just like how if you know Spanish, you can kind of sort of understand Italian, but the words look slightly different. If you know English, parts of German sound suspiciously familiar. In the same way, Python and Ruby and C and Rust all have these 4 types of statements as their main things that you write when you write a program, but they're all going to do them slightly differently with slightly different syntax. Colons versus curly braces, or parentheses required or not, or the word then appearing somewhere. But they're all going to work fundamentally the same way. So my goal is for you guys as programmers not to focus on learning how these instructions work in one particular language, but instead learning how to think about any task you want to do in the real world and describing it just as a chain of saving some information in a place as an assignment, or performing some action on that data, either those places you saved, pulling them out and using them, or just raw data, kind of the verbs of your program. What is it you're doing? Conditionally saying, if something is true, if something has happened, then do these instructions, either a function, one of those verbs, or just a chain of these other statements. And finally, a loop saying, as long as some condition is true, something is still happening, keep doing something over and over and over again. Every program is just an exercise in finding a way to take whatever real world thing you have and representing it as data that can be saved, assigned into some variable in your program, and then finding the right functions that describe the actions you want to do to that data. Maybe with conditions, if you have to check and make a branching path, there are two options of what to do next. Maybe with a loop, if something has to happen over and over again, or there's a long sequence of repetitive things you only want to write out once. But these 4 building blocks are everything you need to write a program. And there's a lot of subtlety to this. Most introductory programming courses take more than a month just to get through these 4 sentences. But as long as you keep in mind that this is the big picture, it becomes much easier to see how all of these pieces fit together. So that is my introduction to computer science and how we got to where we are today. Hopefully this gives you a good perspective on how programming languages work and why they are designed the way that they are. From here, we're going to start looking at the different simple instructions that we can write in Python. So I hope you look forward to that. I will catch you in the next video.